Thank you, Professor Dehnen, for the very informative talk with on multinary clusters with very interesting structures and properties. So, as we can see in the audience reaction, we do have a lot of questions that they have asked. To begin with, I'll pick up something very primary about the synthesis of these clusters. So, how easy or challenging is the preparation of these clusters? Also, if you could comment on the room temperature stability of the clusters.
Yes, I'm happy to answer that question. And maybe I can just use this slide here, then I don't lose time in switching back and forth. And I can tell you that this is very much dependent on the cluster type you're talking about. So let's start with these ones. This is a more or less normal organometallic reaction, and this is pretty easy to do. So you can do this, well, all of these reactions can be done at room temperature conditions, but these here are the least air sensitive ones. So it's pretty straightforward and you have fantastic yields. If you go to this side, then you will go to these ionothermal reactions, which require a little bit of temperature, not too much, but maybe 80 degrees, and you have to use sealed ampules. So it's a little bit more complicated. And the most challenging kind of synthesis is certainly for these metal-like compounds, since you can guess that a metal doesn't want to be in a negative oxidation state. And once you force it to have a negative oxidation state, it wants to get back. So you will have to take great care of no oxygen being around, no water being around. And so these have to be strictly inert conditions. And well, we use glove box techniques, we use Schlenk line techniques, and with this, it's very easy to do, but you have to be trained in this technique. And yeah, you ask for the room temperature stability. All of the clusters I've shown you here during my talk are room temperature stable. Some of them may be a little bit light sensitive, like these tellurium mercurites, as you may guess, but all of them are temperature stable, but all of them are kinetic products in terms of the much more stable binary compounds like salts or metals or the homometallic metals elements. But this is a term in terms of oxidation sensitivity. So most of the compounds you're producing are air stable, air sensitive, but thermally stable.
Okay. Thank you, Professor Dehnen. So another question I would like to pick up is a very preliminary question or a basic question on nanoclusters and nanoparticles. Could you please explain the difference between nanoclusters and nanoparticles?
Yes, well, for this, I may go back, actually. Let me see whether I can get out of this presentation somehow. Yes, I can. So let me just switch back to one of my first slides where I showed this difference. And I hope that you can still see my slides.
Yes.
You can?
Yes.
Is it the right mode? Because it always switches back to this referent mode, but I hope that it's fine. Okay, here we go. So if you look at this slide, you will see that there is a difference in general size. So they overlap at some point. You will have a size regime for maybe, because of the number of atoms being involved, there's a size regime between half a nanometer and 3 nanometers that has been reported for cluster molecules. And then you would probably end up or go further with the nanoparticles. And the reason for this regime is that after or for bigger molecules, you will get into a situation where the atoms are not longer defined. So you will have disorder, a lot of disorder. They get more and more ill-defined. And this is then the point where we would speak rather about nanoparticles. So the largest clusters are not on this slide. The largest clusters I know of that have been crystallographically determined with specific atomic positions that you can really define are in the range of some 400 atoms, maybe 400 or 500 atoms. Then you are really at the end of what is doable for atomically precise molecules, and everything that is not clearly precisely defined, as you can see here, would be something I would call a nanoparticle. Yet I have to admit that this is probably also a little bit a matter of interpretation and a matter of taste. A cluster in the size of 3 nanometers could also be called a nanoparticle, but then it's a nanoparticle with atomic precision. So here you are in a range where you need a bit of definition, and you should probably go and have this definition along with your, for example, publication to be clear.
Thank you, Professor Dehnen. So another participant is specifically interested on lanthanide chemistry. And the question is, are you able to achieve higher coordination using lanthanides in these clusters? The clusters which were synthesized using IL, like ionic liquid mediated synthesis.
I see, for the ionic liquids. Okay, so here I can tell that for ionic liquids, we have not yet reached out to lanthanides, but we are starting right now in a project with another colleague. Lanthanides are not so chalcogenophilic, so they rather prefer having oxygen or nitrogen in their coordination sphere, or metal atoms, as you've seen in this slide, for example. Yet we know that there are coordination networks, for example, with lanthanides, and some of them have even been formed with ionic liquids, so ionothermal approaches, but most of them stem from chemistry in solution or hydrothermal chemistry in water or protic solvents with oxygen coordination. So metal organic is well known, oxygen coordination and nitrogen coordination is well known, and everything beside oxygen or below oxygen in the periodic table is more challenging, but it's not excluded. And as I can tell you, as a sneak preview, we are into that chemistry now. And this is interesting in terms of luminescence, of course, and also in terms of catalysis.
All right. Thank you. So another question, Professor Dehnen, is on the application part of these clusters. Can these clusters be used in metal organic framework systems? And have you ever tried to prepare them in a composite form with MOFs, COFs, or polymers?
Okay, yeah, this is a similar question as the one before. So actually, maybe I even have a slide on that, but no, I didn't bring it with me. So if you go back to maybe one of these clusters, maybe I can show you this one again. So you see that we do have network structures or say extended structures here, but these are only composed of these atoms, mercury and tellurium. But what we can do, and this has been done with the chemistry, maybe yeah, I do have a slide on that. I can show better here in this one. In the chemistry with the organoelement precursors, this is somewhere here, we could show that it's possible to react them with metal atoms, for example, and then form coordination compounds that include these clusters, and then have a framework of cluster molecules and this metal atoms, for example, this metal, yeah, maybe I can show you this. So here you can see that these clusters can be used, for example, with carboxylic groups, or can be formed with carboxylic groups. And then just imagine that there is a metal atom here at this place. Then you have the next cluster continuing. And this has been done, for example, with this type of cluster molecules and manganese. So we had frameworks, and then we could show that they also have nice, interesting magnetic properties. So you can, yes, you can use these as nodes in molecular, in metal-organic frameworks, but this has not been the primary focus of our work. But if you're interested, you're welcome and try. And one of my co-workers is actually doing that as well, and then try to include even clusters in the cluster-based morph. But this is then getting pretty complicated in terms of molecular structures and crystal structures. But this is part of our fun, of course.
All right. Thank you, Professor Dehnen. So I'll take up a couple of more questions, if that is fine with you.
Yeah, absolutely.
All right. So a participant has a question on thermal stability, a part of which you may have already answered previously. So at which temperature these clusters show stability? And if we change the temperature, is there any effect on the aromaticity of these clusters?
Okay, so in terms of aromaticity, the answer is that we cannot tell yet, because the aromaticity has only been proven by quantum chemistry. The aromatic properties have been on metal clusters, and they have been the most effective at bismuth clusters. And you can imagine that for bismuth, it's really difficult to have an experimental proof, as we have no NMR handle. It is no Mössbauer core or whatever. So it's really difficult to prove in an experimental manner, although we are doing that in an indirect way now. But so far, we just calculated that. In regards of the temperature as such, I can tell you that these clusters can be, maybe I got out of that, can be even molten without decomposition. And this is something I couldn't show you for the sake of time. But here you see that easily. What we can do, for example, with these white light emitting clusters is that we melt them, and you have single crystalline compounds in the beginning, you melt them, they get amorphous, but you can show by NMR spectroscopy that they are still the same. So you have temperatures of around 200 degrees C or 150 degrees C to melt them, and they easily stand it. And this is valid to these clusters, and this is also the case for the ionothermally approached clusters. The zinc clusters would decompose before that, so they will be stable to until, I don't know, 40 degrees maybe, or 50 degrees. But for this one, you can even form glasses from these crystals.
Thank you, Professor Dehnen. So in the interest of time, I'll take up one final question, and this is related to the journal. So it's actually two questions. So does inorganic chemistry accept completely theoretical work? And because you say that reviews will be part of the workflow recently,
Yes.
so are there any specific topical areas on which you are interested to take reviews on?
Yeah, so this is a very good question. Thank you very much. And thank you very much for all questions. I forgot to say this especially, but I'm very happy to answer all your questions. So first of all, maybe I start with the latter. So reviews is new for us. So what we are going to do for the first reviews is that we invite reviews, so specific authors to invite and submit one, but we will also accept proposals in the near future. So you can please look up our website regularly, then you will find this hint that we will accept proposals for review articles, and then upon approval, you will be invited to send a full review. The topics are, of course, everything which is topical for inorganic chemistry, and you saw the scope on this slide. Let me see, did I say something about the scope on one of the slides? I said that in words. So we have all kinds of inorganic compounds that we publish in inorganic chemistry, and for all of these you may have interesting review article at hand. The first question was about theory. Yes, we also publish purely theoretical work, yet we like if the theoretical work is not too hypothetical. So this I have to say, if it's just something that comes from the top of your head, but if it's very reasonable, it's fine. But if it's just a random composition of atoms to form, don't know, a cluster compound that may never be realized in the real world in a lab, then we might be a little bit more critical. So we acknowledge and we invite you to send us your best theoretical work. It's no problem to handle that and to publish that in inorganic chemistry. And this is different from former times. I know that has changed, but it should be related to some urgent question. And this is maybe something I'd like to give you as the last statement on the journal. For now, the question that you should ask yourselves before you submit a paper to inorganic chemistry is, do you answer a question that is connected to inorganic chemistry in your paper? So this is the only real precondition. It doesn't matter which method you take to answer this question, but it should be connected to an inorganic chemistry question, because we all want to solve these questions in our community.
All right. Thank you, Professor Dehnen. I think it was a very engaging Q&A session, and the audience loved it. There are still so many questions to be answered, but in the interest...
Yeah, so feel free to reach out to myself via email if you're really interested. I'm happy to answer your questions also after this talk. And yeah, I enjoyed very much being here and talk about our chemistry and the journal.
Thank you, Professor Dehnen. So I'd request Kunal to please take over.
Thank you, Mihir, and thank you so much, Professor Dehnen. And as we can continue to see, there are so many questions that are left, and we really apologize to some of our audience members that we are not able to take up your questions. But as Professor Dehnen mentioned, if you're really interested, please do drop her an email, and I'm sure she'll be happy to come back to you. So with
Absolutely.
that, let me close out the session. So this is bringing us to the end of today's session. We hope that you have enjoyed this broadcast. We invite you to view the edited recordings from the past events in the ACS Science Talks library. At the end of the session, you will receive a brief survey. Kindly share your feedback with us so that we can continue to improve and serve you better. We would be reaching out to all the attendees of today's session if they want to get certificates from ACS. On behalf of all of us at ACS, thank you so much for joining us today. We hope to see you again for more ACS events. Until then, stay safe and healthy.
Thank you very much again. Bye-bye. Stay safe, everyone.